and myself will explain about the PID control in pitch wind turbine. So before that, let me introduce our members first, which is Noorashikin, which are Noorashikin binti ZULARIFFIN, Muhammad HAZIQH bin Muhammad RIZALLUDIN, NAJIHAH binti Abdul RAZAK, and me myself, FARHANAH binti Muhammad FIRDAUS. So let's proceed to our presentation. Next. So a PID controller is a device that uses a control loop feedback mechanism to control process variables such as pressure, temperature, and other else. So this device is commonly used in industrial control applications. So it stands for proportional integral derivative. It is a combination of proportional control, integral, and derivative that assists the unit to recompense the changes within the system automatically. So the PID controller used in this project is to improve the performance of the wind turbine other than the system without the wind turbine, system without the controller. So next, I will pass to my friends.
Okay, so I will continue about the problem statement. So this project focus on the load that cause fatigue and vibration in blade. So there will be a different type of load that the blade will face. Here there are three load that I state, which is aerodynamic load, centrifugal load, and gravitational load. Okay, these all three loads will resulting in degrading rotor blade of wind turbine. So by putting pitch controller, it will prevent this to happen, which is the degrading of rotor blade. So why? Because pitch controller able to tune at the angle of the wind turbine rotor blade in or out of the wind. Okay, and then next we'll proceed to my fellow friends.
Okay, so I'll proceed with the application. So the PID is often applied in a variety control problem, which it works in a decent way without any adjustment or turning. So PID also used to control or regulate flow, temperature, pressure, level, and many other industrial processes that require automatic process control. It also used in wind turbine system to control and monitor the wind speed across the blade, which is to ensure all the wind conditions are in safe operation.
Okay. Next, I have explained about the application also. So basically, the rotor that connects to the main shaft spin a generator to generate the electricity when the energy in the wind turbine turns 2 to 3 blades around it. So the PID controller will regulate the rotor motor of a variable speed wind turbine by adjusting the blade pitch angle, in which the PID controller will control the blade pitch angle, in which it will adjust the aerodynamic torque of the wind turbine when the speed is above the rate speed. Next, my friends will explain about the block diagram.
So basically, this is the block diagram of a normal system wind turbine. As you can see, this is a closed loop system. There will be a turbine that will catch the wind, and then the generator that will generate the electric power, and then the power transducer controller. It divides into two controller, which is pitch actuator and your actuator, and then it come back to the turbine to in order to measure the power needed. Okay, next. Okay, so basically I will explain the first two working principle from that system previous. So the first one is the controller. Okay, the controller will be starting use when the process start. When the turbine capture the wind, then the controller will check the turbine's power output, and if the power is too high, then it will send a signal to the blade pitch. Then the blade pitch will turn slightly out of the wind while adapting the attack angle. So the next one is actuator. It divides into two actuators. First one is pitch and second one is the yaw. Okay, pitch is the function is to turn the blade along their longitudinal axis when the signal has been received from the controller. So this explains that dynamic behavior between pitch demand from the pitch controller and measurement of pitch angle. So while the yaw actuator is used for power regulation, it is responsible for rotating the nacelle around the tower axis, resulting in increasing the energy capture through pointing rotor swept area. Okay, the next part will explain by HAZIQH.
So I'll explain about the working principle of the plant or system. So the plant in this closed loop system is the wind turbine that catch the wind. So the input will cause the turbine to react in a way that will supply the output values that are ideally close to the input values. So all of the subsystem in this PID controller are mathematically expressed as a transfer function. So next is sensor. So sensor is a device that can measure the output variable to be controlled. So after the electric is generated at the generator from the wind turbine, so it will enter into the power transducer. So before it goes to the controller, so the sensor will measure first the response of the power.
Okay, so next I will explain about the transfer function. The first one is the pitch actuator model. So this is the initial parameter of the wind turbine, which is the rated generator powers and also the rated generator speed. The third one is rated turning speed of rotor, wind turbine blade radius, reference pitch angle, rate of change of pitch angle, control accuracy of pitch angle, damping coefficient, and lastly is drive train inertia. So on the left side, on the right side is the values of the parameters. Okay, so for the pitch actuator model, the change in pitch angle is given as the d beta over dt is equal to the reference pitch angle minus the beta over tb. So we do the rearranging, so we can get t beta dot d beta over dt plus beta is equal to the reference pitch angle. So this equation we let it into equation 1. So by applying the Laplace transform, we can get that tb dot t beta dot b beta plus beta is equal to the reference pitch angle. Get that one, the ratio of the beta over the reference pitch angle. So from equation 1, we can get that t beta is equal to 0.5 by substituting the value, and we substitute the value of 0.5 into equation 2, and we can get the ratio of the beta over reference pitch angle is equal to 1 over 0.5 s plus 1. So the next transfer function is on the drive train model. Basically, there is 11 parameter used for the transfer functions of drive train model. So the dynamics of the drivetrain are described as the equation below it. So by applying the Newton's second law of motion, we can get that dw over dt is equal to t minus bw. So we apply the Laplace transform and we can get jws equal to t minus bw. And we rearrange it so it goes into the equations of w over t is equal to 1 over js plus b. So basically, this ratio equation is required for the first order transfer functions of drivetrains, as it can be presented as w over t is equal to 1 over b over jb dot s plus 1. So we substitute the values as in table 5.1, which is the pitch actuator models table value, and we can get the ratio of w over t is equal to 0.5 over 0.3575 s plus 1.
So I will explain about the block diagram in Simulink model. So the right picture show the Simulink model of PID controller, and the left picture shown the Simulink model without PID controller. So at the bottom of the slide, we can see two graphs of without not graph, the unit step response of without PID and PID controller. So in this graph, we can see that the rise time, settling time, and peak overshoot of without PID is higher. So when we added PID into the system, it becomes smoother. So next. So this is the comparison of unit step response for all PID controllers, which means the changes of PID parameters. So next. So as I said before, the without controller has high rise time, high settling time, and high peak overshoot. So when we added PID controller into the system, the rise time, settling time, and peak overshoot become low. So both of them is portrayed in light green and gold. So then I try to no, then we try to change the PID parameters. So PID parameters will bigger than the default one. So it portrays in light blue line. So the response show that the rise time is higher. No, the rise time and settling time is higher than the PID default. But the peak overshoot is lower. When we change the PID to the bigger than the default, the rise time will have almost the same with the default, but it have the lower settling time and higher peak overshoot. So next. So other than that, we also change each of the parameters. So the first one is proportional lower than default. It portray in purple line, and we get that rise time. The rise time is higher than the default one, but the settling time and peak overshoot is almost the same as the PID default. So when the proportional is bigger than the default, the rise time and settling time is almost the same as the PID default, but have higher peak overshoot. Then we try to change the integral. So integral lower than default shows that we have a rise time that almost the same with the PID default, and higher settling time and lower peak overshoot. While integral that bigger than the default show that still have the same almost the same rise time, but lower settling time and higher peak overshoot. So when we change the derivative lower than the default, so the rise time is increased, but the settling time and peak overshoot is almost the same as the PID default. But when we change the derivative bigger than the default, so we get that rise time and settling time is almost the same with the PID default, but higher peak overshoot. So what I can conclude from these result is first, it is not necessary to change all parameters to get final results. Other than that, each parameters has their own effect on the unit step response. So in this case, PID with higher integral gave the better results than other types of PID. So next.
Okay, so for the conclusion, the wind turbine pitch control system mathematical model are developed and simulated with a PID controller that by using the MATLAB software. This is to achieve the optimal response, and it is easier for understanding the pitch system regulation and in maintaining the reliability of the output power of the wind turbine. Also, the last part is the PID controller is useful as it can control and also regulate the wind speed. This is because it greatly improves the unit step response of the wind turbine, and also PID controller with higher values of integral is chosen by doing the experiment. That's all from us. Thank you.